Assalamualaikum warahmatullahi wabarakatuh. My name is Nira Mawangi Sarif. Today, I would like to present my master research titled A Discrete Time Terminal Sliding Mode Control for Autonomous Underwater Vehicles. This is my presentation outline, where I will start with Introduction on Autonomous Underwater Vehicle known as the AUVs, research objectives, mathematical modeling of AUV system, controller design, result and analysis, and also discussion. I would like to start my presentation with an introduction on AUV system. AUV is underwater robot which operate autonomously. It consists of multiple measuring devices and also sensors. Those are magnetometer, accelerometer, barometer, and dropper velocity log. For the sensors, those are optical sensors, pressure sensors, and temperature sensors. Due to the various advantages of AUV system, such as less operational cost, safe life, and low environmental impact, the application of AUV system has been implemented widely, especially on pipeline inspection, oil and gas exploration, and offshore surveys. The research objectives can be divided into three. Firstly, to improve the system state convergence performance from finite to infinite time. Secondly, to reduce the chattering effect in the control input. And lastly, to evaluate the performance of AUV motion via comparison with discrete sliding mode, discrete terminal sliding mode, and MPC controller. This is the mathematical modeling of AUV system. The motion of AUV can be described into a 6 degrees of freedom. Those are surge, sway, heave, roll, pitch, and yaw. All these 6 degrees of freedom can be combined and decoupled into 3 subsystems. These subsystems are speed, steering, and diving. For this research, we only focus on a diving motion of control, in which, for a diving motion of control, there are only 2 degrees of freedom involved. Those are heave and pitch. For discrete terminal sliding mode controller design, it consists of the 4 steps. The first step is selection of the sliding surface. The sliding surface used for discrete terminal sliding mode is a nonlinear type. Second step is selection on discontinuous component. For this research, the constant plus rate reaching law is implemented to the controller design. The step 3 is designing the control law, and the final step is stability analysis of the design controller. The stability of the design controller can be analyzed mathematically. This is the comparison of the controller design. As I mentioned earlier, the proposed controller, which are discrete terminal sliding mode, will be compared with a discrete sliding mode and also the MPC controller. For discrete sliding mode and discrete terminal sliding mode, they are from a same family, which is sliding mode control. However, the difference are in terms of a sliding surface. For discrete sliding mode control, the linear type sliding surface is implemented in the control law, while for discrete terminal sliding mode, the nonlinear type sliding surface is implemented to the control law. For the reaching law, the same reaching law is implemented to both of the sliding mode family. However, for the MPC controller, there are no sliding surface, neither reaching law implemented to the control law design. This is the result of the convergence performance for the discrete sliding mode, discrete terminal sliding mode, and MPC controller. From this slide, it can be seen that discrete terminal sliding mode, which is formed from a nonlinear sliding surface, gives fast settling time without high oscillation on the control output. The MPC controller also provide fast settling time. However, the frequency oscillation is considered high. The discrete sliding mode controller with form from a linear sliding surface, on the other hand, shows a longer settling time without high frequency oscillation. In this slide, the reaching time of the system state to the sliding surface is presented. As I mentioned earlier, only sliding mode control family used a sliding surface. For this reason, only discrete sliding mode and discrete terminal sliding mode presented in this slide. From the result, we can see that discrete sliding mode with a linear sliding surface gives faster reaching time to the sliding surface. However, for discrete terminal sliding mode, which is formed from a non-linear sliding surface, gives a longer reaching time to the sliding surface. This is to say that discrete sliding mode offers strong robustness against perturbations and external disturbances than discrete terminal sliding mode. The control input for discrete sliding mode, discrete terminal sliding mode, and MPC controller is presented in this slide. It can be seen that discrete sliding mode control gives large initial control effort in comparison to discrete terminal sliding mode and MPC controller. The discrete terminal sliding mode, on the other hand, gives smaller initial control effort in comparison to discrete sliding mode and MPC controller. In this slide, the chattering effect induced by discrete sliding mode and discrete terminal sliding mode is presented. It can be seen clearly in this slide, discrete terminal sliding mode presents smaller chattering effect than discrete sliding mode. The chattering effect is undesirable phenomena because it will lead to instability to the control system and also high wear and tear to the actuator. The discrete terminal sliding mode, which use a non-linear sliding surface, while discrete sliding mode control use a linear type sliding surface in a controller design. The conclusion is, this is the conclusion for this presentation. Discrete terminal sliding mode gives a better control performance, finite convergence property, imposing small initial control effort and small chattering effect. However, longer reaching time to the sliding surface in comparison to discrete sliding mode. Longer reaching time of the discrete terminal sliding mode degrade the controller robustness against perturbation and external disturbances. Shorter reaching time with a small initial control input and small chattering effect can be obtained by combining the non-linear sliding surface presented by discrete terminal sliding mode and linear sliding surface presented by discrete sliding mode controller together.